Hi. So, to find the capacitance of a spherical capacitor. A spherical capacitor is having two spheres, the spherical conductors. The inner sphere can be either solid or hollow, and the outer sphere is hollow one. Okay, now we know that capacitance is equal to charge per unit potential. So for finding capacitance we need to find these two quantities, charge and potential. So we will assume that, let us assume the charge on inner sphere is, the charge on capacitor is plus Q, and outer sphere is minus Q. Therefore, charge on the capacitor is plus Q. Charge on the capacitor is equal to plus Q. So let me draw it again. You have plus Q charge and there you have one outer sphere. So you have assumed that charge is plus Q. Now you will find value of potential due to this charge. So let me take a Gaussian surface inside at any distance r. Now the inner sphere has radius r1 and the outer sphere has radius r2. So let there be a Gaussian surface of radius r. Therefore, from Gauss's law, flux phi is equal to, since flux phi is equal to, okay, E dot ds, and this is equal to charge enclosed upon epsilon naught. This is from Gauss's law. Okay. Now electric field can be equal to charge enclosed is Q upon, and the surface area with radius r is equal to 4 pi r square, and this is your epsilon naught. So you obtain electric field. Now next step next, since you know the relationship between potential and electric field, potential is equal to minus of E dot dr, and you will be integrating this. So under proper limit, proper limit, so this is equal to minus, and electric field is equal to Q upon 4 pi r square epsilon naught, and this is your dr. So this is the positive work, because when you, and this is the work from point A up to point B, because this is force applied by electrostatic charge only, and the like charges will repel. If you place any test charge of positive nature, it will be repelled along radial direction. So field is along this direction, displacement dr also is in direction. So electric force is equal to this much from point A to point B. But here we are to find potential at this point, and potential is equal to work done by external agency at any point. So, and this is work from A to B, and from external agency it will be from B to A, just opposite. From internal agency, from electric forces, you will be displaced from A to B, and we have to find work from external agency, so it will be from B to A. Now, from point B to A, and that is your distance R2 to R1. This is equal to minus R2 to R1, and let me take all the constant terms outside. So let me take all the constant terms. Q is a constant, 4 pi is a constant, and epsilon naught is a constant. So here you are remain with r power minus 2 dr. Therefore potential V is equal to minus Q upon 4 pi epsilon naught r power minus 3, okay, r power minus 1, because it is your minus 2 plus 1 divided by minus 2 plus 1, and it is under limit R2 to R1. Therefore we obtain potential minus Q upon 4 pi epsilon naught, and this minus minus becomes plus, and here you have 1 by R under limit R2 to R1. So this is your potential. Now putting the value of potential and charge in equation 1. Now on putting values of Q and V in equation 1, we get that C is equal to Q upon 4 pi epsilon naught 1 by R1 minus 1 by R2. Here Q and Q is cancelled, therefore C is equal to 4 pi epsilon naught upon R2 minus R1, and this is equal to, let me take the LCM in the numerator, R1 R2. So this is capacitor of a spherical capacitance of a spherical capacitor. Okay, now many a time you will be having a single spherical capacitor like that of Earth. Earth has a single sphere and it has capacity to hold charges. It has large magnitude of charge on the surface of Earth. So for such a single sphere, the capacitance of a single sphere. Now here you will take R2 as infinity and R1 as R. So you get, therefore you get C is equal to 4 pi epsilon naught R1 R2 upon, when R2 is tending to infinity, so R1 becomes negligible. So let me remove delete R1 from denominator and we get R2 only. Here R1 is very less than R2, therefore R1 is removed from denominator. Now you cancel the similar terms from numerator and denominator and you get capacitance of a sphere is equal to 4 pi epsilon naught r. And you can see that it is depending only on dimensions, it is not depending on charge, it is not depending on potential. So it depends on dimension. It depends on, due to this epsilon naught, it depends on nature of dielectric that is surrounding this sphere. Nature of dielectric surrounding the sphere. Now, in the same way we can find capacitance of a cylindrical sphere, cylindrical capacitor. Okay. So you can see that the name of capacitor is as per their shape. So next, capacitance of a cylindrical capacitor. So let me draw first of all a cylindrical capacitor. It will be having a central cylindrical conductor. This is your cylindrical conductor. It can be solid or hollow. Solid or hollow conductor. Now it is surrounded by a hollow cylindrical conductor. This outer one is hollow cylindrical conductor. Now this forms a capacitor, and we are interested in finding capacitance of this cylindrical capacitor. So let me draw again. So this is the inner cylinder with radius. Its radius is R1. And there is an outer cylinder with radius R2, and let the length of this cylinder is L. Length of this cylinder is L. Let me write everything. The radius of inner cylinder is equal to R1. The radius of outer cylinder is equal to R2, and the size of the height of cylinder is L. The height of the cylinder is equal to L. Now let us assume that the charge on inner cylinder let me. So let the charge on inner cylinder is equal to plus Q, and that of outer cylinder is equal to minus Q. Now we know that we have electric field in outer space only. So for outer sphere, if we have charge, then also it will have electric field inside the hollow is equal to 0. Therefore, electric field, since electric field only resides outside, therefore we have E only due to plus Q charge. So next step is, stepwise we will be doing, since capacitance is equal to, if we take capacitance is equal to C, then it is equal to Q coulomb upon V volt. So we have assumed the charge on the capacitor is equal to Q. So Q we know, and my next step is to find value of V. So I will be finding the value of V by knowing what the electric field is in the given region. So let me take first of all a Gaussian surface, let me take a Gaussian surface of any size. Let me take a Gaussian surface of size equal to the size of height of the cylinder itself, and which is having radius R. For electric field, let there be a Gaussian surface of height L only and radius R. So electric field using Gauss's theorem, therefore using Gauss's theorem, phi is equal to E ds is equal to Q enclosed upon epsilon naught. Now we have three surfaces. You can see we have three surfaces. This surface 1, surface 2, and your this cylindrical surface, the surface 3, curved surface. And flux lines are going from all these three surfaces. So flux can be divided into the three parts, phi 1 plus phi 2 plus phi 3 is equal to E ds cos. Now you can see field is along radial direction and area vector is along, ds is along at this very point perpendicular direction. So angle is 90 degree along the two circular surfaces. Angle is your, here also your surface area is directed along downward direction, but electric field is along radial direction. So here angle becomes 90 degree. So along the two surfaces, circular surfaces, your 1 and 2, cos theta is 90 degree. So EDS 90, EDS cos 90, and flux through your curved surface is equal to EDS cos 0, and this is Q enclosed upon epsilon naught. Now these terms becomes 0, therefore E and surface area, we are finding electric field at this very point at a distance r at point P. At P, okay, electric field at point P. So we will find surface area at that very point. We will integrate, okay, let me delete this. We will integrate all the EDS. We will integrate on whole the surface, and we will get that E into whole surface area is equal to surface area, curved surface area, this curved surface area. Now when you make a cut on this curved surface area, it will open out and you will get a rectangular sheet of this shape, and so when it will open up here with radius r, so it's this size, this length will become 2 pi r, and this is taken as L. So your surface becomes equal to 2 pi r into L, and here it is okay, and this is equal to your charge enclosed Q upon epsilon naught. So therefore electric field becomes equal to Q upon electric field where? Electric field at point P, only. And so why? You know that at Gaussian surface, which is symmetrical, so if you have electric field at point P this much, so at every point the same electric field will be there. So electric field will be equal to 2 pi r L into epsilon naught. So we find E. We know charge, we find E. Now our next step is to find potential. Since potential V is equal to minus EdR. Okay, let me delete this, minus EdR under proper limit. From where to where? Now look, we have a positive charge. Here, let me take different color. We have a positive charge. So, this electrical force is doing work in sending any charge away from this positive charge. It will send any discharge of same polarity away from it, and it will be sending from a near point A to far point B. This is the electrical force. But our potential is work done by, our potential is equal to work done by external source. So if electrical force is doing work from A to B, so external any agency will be doing work from B to A in pushing it inward. So we will integrate it from B to A, and we know that we have radius at B is R2 and at A it is R1, and electric field we obtain Q upon 2 pi RL epsilon naught dr. So let me take all the constant terms outside, and this is equal to your Q upon 2 pi L epsilon naught. All these are constants. So let me integrate 1 upon R dr under limits R2 to R1. Therefore, V is equal to minus Q upon 2 pi R, 2 pi L epsilon naught, and it becomes log R. Integration of 1 upon R dr is log R, and under limit R2 to R1. So this becomes equal to Q upon 2 pi R epsilon naught log R1 minus log R2. Okay, let me delete this log R2. And finally, we have potential minus Q upon 2 pi L into epsilon naught into log R1 upon R2. If you take this minus sign as the power of this log, so you get Q upon 2 pi L epsilon naught log R1 upon R2 power minus 1, and therefore V becomes equal to Q upon 2 pi L epsilon naught log R2 upon R1. So now we have the values of U and V, and we will put these two values in this equation 1. So on putting the values of U and V in 1, we get that C is equal to Q upon 2 pi L epsilon naught log R2 upon R1. So these two are cancelled and C comes equal to 2 pi L epsilon naught upon log R2 upon R1. So this is your capacitance of a cylindrical capacitor. You can see here, in this case also you can observe that it does not depend on charge. Charge is cancelled, potential is also cancelled. Now it depends on only R1 and R2 means dimensions. It depends on dimensions. It also is depending on length, and it depends on nature of the dielectric placed in between the two plates. So it depends on number 1 dimensions, number 2 the dielectric material, in between the plates. Okay, now I conclude.